Good evening. Hello and welcome to NPTEL classes. Here is Chemistry Detective to solve Chemistry class 11th NCERT problem from unit 2nd, that is structure of atom. Let me make you understand today's problem. We have to calculate wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. You might have got clue that today's problem is based on concept of line emission spectrum of hydrogen. Line emission spectrum of hydrogen is very important topic to understand Bohr's model of atom. Let me go through this line emission spectrum of atom in form of story so that I will put in your mind all the necessary ideas that I require to solve this problem. Imagine we have hydrogen, we have sample of hydrogen in discharge tube at low pressure and high voltage. What happens under these conditions? Hydrogen atoms will be present in excited state. So, in this discharge tube, we now have hydrogen atoms which are present in the sample of hydrogen in excited states, in their excited states. That is, for example, if I will take, there are 3 hydrogen atoms in sample, one hydrogen atom will be present in excited state, second hydrogen atom will also be present in excited state, third hydrogen atom will also be present in excited state. I mean, electron which is present in n is equal to 1 first orbit will now be present in n is equal to 2, let us suppose for hydrogen atom 1, in n is equal to 3, let us suppose for hydrogen atom 2, in n is equal to 5, let us suppose for hydrogen atom 3rd. So, in different hydrogen atoms, excitation level to which this electron occupies is different depending on how much energy hydrogen atom has absorbed during excitation. Some may absorb large energy, some may absorb less energy. Accordingly, excitation levels will be different in different atoms. But in excited state, hydrogen atom is unstable and this electron has to return back to n is equal to 1. In hydrogen atom 1, we have considered that excited electron is present in n is equal to 2. It has to back return to n is equal to 1. In hydrogen atom 2nd, excited electron is present in n is equal to 3. It has to return back to n is equal to 1. In excited hydrogen atom 3rd, electron is present in 5th excitation level, 5th energy level. It has to return back to n is equal to 1. But on return, this is important point, on return of this electron from excited state, higher energy level, to ground state n is equal to 1, it has choice. It can follow multiple paths, it can follow multiple routes. For example, in hydrogen atom third, I said that excited level is, for an electron excited level is n is equal to 5. Now it has to come to n is equal to 1, but it will follow multiple paths. It has options, it has choice. It can come directly from n is equal to 5 to n is equal to 1. It can come from n is equal to 5 first to n is equal to 2, then from n is equal to 2 to n is equal to 1. It can come from n is equal to 5 to n is equal to 4, then directly from n is equal to 4 to n is equal to 1. It can come from n is equal to 5 to n is equal to 3, then directly from n is equal to 3 to n is equal to 1. So a single electron present in fifth excited state has multiple routes available to come back in n is equal to 1. Each route, each pathway involves electron jump or electron transition. So different routes will involve different electron jumps, different electron transitions, and when we will record electromagnetic radiations emitted during de-excitation, we will get series of lines, we will get number of lines, and each line will correspond to a photon of particular wavelength, of particular frequency, of particular wavelength, or more commonly used particular wave number. As different lines have different wave numbers, it means different transitions involve different transition energy difference between higher energy level and lower energy level. And it means energy levels involved in a transition have particular energy, have fixed value of energy. So this idea basically supports idea of quantization of energy, because each line has a particular wave number. It indicates that each transition has particular transition energy, which has fixed transition energy, which is possible only when energy levels involved in this transition have fixed or definite energy. So it supports idea of quantization of energy, that electron in an atom cannot have any values of energy, it can only have fixed values of energy. Its energy values are restricted to only certain values. With these ideas, I will be able to solve this problem. Let me give you data in form of figure, how we get multiple lines in line emission spectrum of hydrogen. Suppose this is first energy level, first orbit, this is second orbit, this is third orbit, this is fourth orbit, this is fifth orbit, and let us imagine this is orbit at infinity. This is orbit at infinity. First orbit, visualize it as a ladder, and each step of ladder has fixed value of energy. Energy cannot take these values. We cannot imagine energy to take value in between n1, n is equal to 1 and n is equal to 2. Energy can have either value this or this or this or this or this or this, fixed values of energy, quantization of energy. Now, for any hydrogen atom, excited electron will be present in n is equal to 2 and will return to n is equal to 1. For some other hydrogen atom, excited electron will be present in n is equal to 3 and will directly come in n is equal to 1. Likewise, n is equal to 4 to n is equal to 1. Likewise, n is equal to 5 to n is equal to 1. Likewise, n is equal to infinity to n is equal to 1. These are different pathways, different routes for an electron in order to return from excited state n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to infinity to n is equal to 1. Or electron can come from n is equal to 3 to n is equal to 2, n is equal to 4 to n is equal to n is equal to 2, n is equal to 5 to n is equal to 2, n is equal to infinity to n is equal to 2. This is also possibility. Then from here it will come to n is equal to 1, which I indicated here. Similarly, electron can come from n is equal to 4 to n is equal to 3, n is equal to 5 to n is equal to 3, n is equal to infinity to n is equal to 3. This is one more series of lines. Similarly, electron can come from n is equal to 5 to n is equal to 4, n is equal to infinity to n is equal to 4. At last, electron, if I will show one more line here, n is equal to 6, electron can come from n is equal to 6 to n is equal to 5, n is equal to 7 to n is equal to 5, n is equal to 8 to n is equal to 5, n is equal to infinity to n is equal to 5. Now, if I will record, here also these are electromagnetic radiations which will be emitted once excited hydrogen atom in a sample of excited hydrogen atoms in sample of hydrogen return back to ground state. And if we will record these electromagnetic radiations on photographic film, we will get separate line, we will get series of lines, first series, second series, third series, fourth series, and now fifth series. Each series, for first series lower energy level N1 is 1, for second series N1 is 2, for third series of lines N1 is 3, for fourth N1 is 4, for fifth series N1 is 5. Lower energy level N1 for first series of lines is 1, for second series of lines is 2, for third series of lines is 3, for fourth series of lines is 4, for fifth series of lines is 5. And N2 will be higher energy level, here will be greater than 1, that is 2, 3, infinity. Here it will be greater than 2, 3, 4 up to infinity. Here it will be greater than 3, 4, 5 up to infinity. Here it will be greater than 4, 5, 6 up to infinity. Here it will be greater than 5, 6, 7 up to infinity. Each series of line is named after its discoverer. First series of line is named as Lyman series. First series of line is named as Lyman series. Second series of line is named as Balmer series. This is Balmer series. Third series of line, here this question is based on this series, Balmer series. Third is Paschen series. Fifth is Brackett series. First is Lyman, second is Balmer, third is Paschen, fourth is Brackett, and fifth is P-Fund series. Lines are divided into 5 series. Each series has been named on basis of its discoverer. First series Lyman series, second Balmer, third Paschen, fourth bracket, fifth Pfund. And for these 5 series of lines, lower energy level is for Lyman 1, for Balmer 2, for Paschen 3, for bracket 4, for Pfund 5. And higher energy levels are greater than lower energy level. For Lyman it is greater than 1, for Balmer it is greater than 2, that is 3, 4, infinity. Since our problem is based on Balmer series, so I will stick to this series of lines, Balmer series of lines. Balmer series of lines. And in Balmer series, lines in Balmer series correspond to return of excited electron from higher energy levels N2 is equal to 3, 4, 5, 6, infinity to lower energy level N1 is equal to 2. And let me show its spectrum here. I will take spectrum of Balmer series. Out of this line emission spectrum of hydrogen, this is complete line emission spectrum of hydrogen, and out of this I will take Balmer series. Let me show here this, and this. This is n is equal to 1, this is n is equal to 2, this is n is equal to 3, and this is suppose n is equal to infinity. Now lines in Balmer series correspond to return of electron from higher energy levels, that is n is equal to 3, n is equal to 4, if I may write here n is equal to 4, n is equal to infinity, to lower energy level n is equal to 2. Here in this jump, in this electronic transition, higher energy level is 3, lower is 2. In this higher energy level is 4, lower is 2. In this higher energy level is infinity, lower is 2. This will be first line of Balmer series, this will be second line of Balmer series, this will be third line of Balmer series. For first line, identify higher energy level, it is 3 and lower is 2. For second line, N2 is 4, N1 is same 2. For series limit, last line in the series, N2 higher energy level is infinity, lower is same 2. Now this is transition energy for first line, this is transition energy for second line, and this is transition energy for third line or series limit. I will write transition energy delta E for first line. For first line, lower energy level is 2, higher energy level is 3. Similarly, transition energy for second line. For second line, I will represent by 2-4. For third line, I will represent by delta E 2-5. And for series limit, I will represent delta E 2-infinity. This is transition energy that will be emitted during transition when electron returns from n is equal to 3 to n is equal to 2, and it is first line of Balmer series, it is second line of Balmer series, it is third line of Balmer series, it is series limit of Balmer series, last line. This is transition energy of first line, this is transition energy of second line, this is transition energy of third line. Obviously, transition energy of first line is less than transition energy of second line, it is less than transition energy of third line likewise. Now we know energy is inversely related to wavelength. Here wavelength will be longest for electron transition from n is equal to 3 to n is equal to 2, which is first line of Balmer series. Wavelength will be largest, followed by 2-4, second line in the series, followed by third line in the series 2, 5. Likewise. Now we have to calculate this. We have to calculate the wave number for longest wavelength transition in the atomic spectra of hydrogen. We have in the problem we have to calculate wave number for largest or longest wavelength transition in the Balmer series of atomic hydrogen. In the problem, we have to calculate wave number, not wavelength. We have to calculate number. We have to calculate wave number. But of what? Of longest wavelength transition in the Balmer series of atomic hydrogen. So we identified it is the first line of Balmer series. So we have to calculate wave number for first line of Balmer series. Now I am at a stage, now I am in a position where from I can identify what I have to calculate. I have to calculate wave number. I have to calculate wave number of longest wavelength transition in the Balmer series of atomic hydrogen, and that corresponds to first line of Balmer series. This is the first line of Balmer series. This one, I have to calculate wave number of this line, first line. I have to calculate this wave number of this line. And let me identify N1 and N2 here. N1, I have to calculate wave number, and for this first I will identify N1, lower energy level. For Balmer series, lower energy level is always 2 and higher energy level for first series is 3. For 3. Now I will use Rydberg equation. Nu bar is equal to 109,677 1 by N1 square minus 1 by N2 square. I will substitute values. This will come in centimeter inverse. I will substitute values. Nu bar is equal to, let me solve it here. So in order to solve this problem, I have to use this equation, that wave number of first line of Balmer series I will calculate by this. Nu bar is equal to R 1 by N1 square minus 1 by N2 square. R here is Rydberg constant and its value is 109,677 centimeter inverse. For first line of Balmer series, N1 is 2 and N2 is 3. Now I can solve this for wave number. Wave number will be equal to 109,677 1 divided by N1 square, which is 2 square, that is 4, minus 1 by 3 square, that is 9. Nu bar is equal to 109,677 9 minus 4 divided by 36. This is for first line. for first line in Balmer. Nu bar will be is equal to 109,677 into 5 divided by 36, and answer will come in centimeter inverse. On solving it comes, I have to multiply 109,677 by 5, then divide by 36, and it comes equal to, nu bar comes equal to 152.9 centimeter inverse. And if I may write it in scientific notation, I will write 1.52329 into 10 to the power 4 centimeter inverse. This is the answer. This I had to calculate wave number of longest wavelength transition in the Balmer series of atomic hydrogen, which I identified is the first line of Balmer series, and for this wave number I got is 1.5 into 10 raised to power 4 centimeter inverse. I may write my answer in SI unit. For this I have to convert centimeter inverse into meter inverse. Multiplying factor will be 10 raised to power 2. I will get 1.5 2329 into 10 to the power 6 meter inverse. This is answer. Both are answers, but one, this is answer of this problem in centimeter inverse, this is answer of problem in meter inverse. Both are correct, but more standard form of writing an answer is in SI unit, which is meter inverse, though wave numbers are usually written in centimeter inverse. Class 11 students, be blessed. This is what I had for you today. See you day after tomorrow, as tomorrow is turn of class 12 students. Take good care of yourself. Allah Hafiz.